Hey, you 13s. Good to see you guys. I'm just going to, I will send you guys the link, view on YouTube. I will send you guys the link to the YouTube video. 2 people already waiting. Yeah, which is nice. Dixon and Tenzi are already there. That's amazing. So I'm going to pause that now. I'm going to pop out the chat so I have access to that, I can close my YouTube video down in order to save on the bandwidth. Let's see if I can move that pop-out window over to my other screen. Can I just have Julian say hello, just to check that Julian's made it? Let's have a look. Is Julian going to say hi? I'll lob it onto the... There we go. Oh, no. Nuts. That's the wrong thing. Oh, Julian's there. Winner. Fine. Cool. Okay. Let's continue. Okay, guys. So today's lesson is on aqueous chemistry. We're continuing with it. We've been looking at redox titrations for the last 2. I know that you guys have got some exercises that you're working on. And we will do some more one-to-one sessions on the Google Meets to be able to address any of those issues that you might have picked up throughout the process. And I will also do some interventions as well, looking at exam questions and with student-specific people who I know are struggling. But if you've got any questions regarding redox titrations, please put them on the YouTube channel, and I'll respond to them if anybody's watching who's not part of my class. Okay, so today's lesson, we're moving on to our next transition metal. So we're moving on to iron today. I love the fact that I did brackets TM in my lesson title and it changed it to TM, like trademark. Oh, crack me up. I need to share my screen. I haven't shared my screen yet. Shared screen, there we go. There we go, we're in, there we go. Okay, so we're doing iron today. Iron. Cool, right, so my laptop is going crazy. The screen connector's a bit dodgy. So 3 learning objectives today, guys. So we're focusing on iron as a transition metal. We're looking at the colors of iron 2 and iron 3. Notice that we are doing this in one sitting. So we've actually got 2 mind maps to create and then input the data into our table context. We're going to look at building reaction equations. We're now getting to the point, guys, where we're starting to see this repetitive behavior repeat so many times that we should be getting to the point where we are building these equations and not having to memorize them. And then it's nice just to know the oxidation of iron 2 and how it has some similarities but differences to iron 3. So, okay, so first one, I'm actually going to do this in an odd way. I'm going to do iron 3 first. I'm hoping that by the end of the lesson, you'll understand why. So, iron 3 plus. Okay, iron 3. I'm actually going to put, I'm going to put Fe3 plus because it's better. Fe3 plus. And here's our beautiful heart. Okay, so the first thing we're going to do, like we did in all of the previous ones, we're going to be talking about the fact that you can have the anhydrous salts of this. So it'd be something like iron 3 chloride. Yeah, now iron 3 chloride, if it was anhydrous, it'd be a white solid. It'll be a pale yellow because you can never have 2 anhydrous, but it's essentially white. And what we're going to do is we're going to take that and we're going to add it to water. So remember, key points to remember here, guys. Everything starts off Hexa Aqua. So first one, we're going to be adding H2O. I'm going to try and make the lines a little bit easier for me to label. So we're going to add it to water, and I'd like you, please, to give me my starting product, please, from that reaction. You can pause the video and have a go at completing its formula. Yeah. So Fe brackets, H2O 6, close brackets, 3 plus. Then we get to pick up its color. So iron 3 plus. Iron 3 plus is yellow in solution. It's a yellow solution. Love it. Nice to include our state symbol. Reminder again, these key points, these key repetitive points. If a transition metal ion complex has a charge, it's going to be aqueous. So this is a yellow solution. Yellow sol. Right, now guys, since we've been doing this now, I want you guys to start taking ownership of this. So the next one is going to be OH minus sodium hydroxide. Yeah, I'm going to put NaOH little. Yeah, I'd like you now to have a go at then doing NaOH excess. Then we step into the ammonia. So we then do, again, trying to make the lines longer. Then we've got ammonia little. Then we go to ammonia excess, concammonia, and then we go to the carbonate. And then add the carbonate ion, sodium carbonate. Right, guys, I'd like you now to take a couple of minutes. Well done, Julian, he knows what he's doing, great. I'd like you guys just to take a few minutes just to fill out what my products are going to be for each of these stages, bearing in mind it is a +3 ion, yeah? Now, I'm going to tell you that iron 2 and iron 3 plus are both very easy. I'm doing them together because they're very straightforward, yeah? And we can make some predictions and then make the adjustments as we do. And I love iron. Iron 2 plus and iron 3 plus are so easy from a transition metal perspective. Right, let's fill them out and see how many you get right. So the first one, we're going to need 3 OH minuses because it's Fe3 plus. I'm going to shrink my pen, I think. Pen's a bit thick. There we go. Aqua trihydroxy complex. And it gains a neutral charge, so it's a solid. And we see a change in color. So nice thing for you to consider is the reason for the change in color. Yeah, it's good to think about that. I'm trying to pick the color that I kind of like. It's that color. That's better. So there we go. So thinking about the reasons for a change in color. Yes, this is a brown precipitate, PPT. It's nice to add that on, just a reminder. PPT stands for precipitate. Next. Okay, what about excess? Now, this is an oddity for the 3 plus world because you would expect, because it's a 3 plus complex, we know it has a lower pH than the 2 plus, pH 3 this. You would expect it to redissolve, but iron 2 doesn't. It produces, it's an oddity. Can I just point out, it does actually redissolve a little bit, but the problem is it's to such a tiny extent that they just don't seem to bother with it. Yeah, irritate. Right. So it's an oddity. Yeah, it's an oddity here, guys. All the other 3 pluses have redissolved to some extent. Yeah, the chromium had a full swap out, a full neutralization going to OH6, 3 minus, redissolved to form a purple solution. The cobalt went through a full swap as well and producing a blue solution. Pink, blue, blue, blue. Yep, a blue solution. This is an oddity. It remains a solid. Now, the best thing is, of course, that the littles with everybody is always the same. So square brackets, Aqua trihydroxy. And I wonder if anyone can recall the reason for this. Put it on the chat if you can remember. I quite like doing it like that. I think it's artsy. Yeah. Next, iron, unlike all the rest, goes through no substitution whatsoever. Iron 3 plus and iron 2 plus go through no substitution or redissolving in any way. Very strange. No, it just doesn't. I know it seems odd, right? But it doesn't. You would expect it to, but it doesn't. So it's yellow, brown, 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 brown. And then the next one, of course, is because it's an iron 3 plus, it actually forms exactly the same product again. The reason, but this one I'm going to add in the extra, the CO2. Yeah, once again, same thing, but we also get 3 carbon dioxides produced as well. So we see tiny bubbles. Tiny bubbles. That's what we see fizzing. But they're really difficult to see. So iron 3 plus. Look at that. Isn't that crazy? It's like the easiest one ever. Just remember that you have one change and then everything else remains the same. How neat is that? I will just mention to you guys that there is another color that I like to teach. EdXL says that you are not required it, but I just don't really believe them. Yeah, Sometimes they often refer to the original color of the yellow solution of iron 3+. They sometimes refer to it as ruby. This is the theoretical color. Now, the reason why, similar to chromium, because it's so acidic, it goes through dissociation. The Fe Hexa Aqua is, unstable, and it's going to go through dissociation in water, and we're going to form Fe H2O 5 OH 1 2+, and 1H+. And just to tell you that this here is yellow. This one here, which yellow did I use? I didn't use the yellow I expected to use. This yellow, yeah, that yellow there, it's not actually yellow. That is the yellow one. That's actually what you're seeing. Yeah, and this one is the ruby red. Yeah, and sometimes they've used questions like this to say, explain how a student could increase the level of ruby color in the solution. And what they would say is add acid. Yeah, if you increase the amount of acid in the system, yeah, we'll push the equilibrium in that direction. So add acid. Add acid. Add acid. So if you add acid, it'll shift the equilibrium from right to left, and you'll see it turn more ruby. In reality, you don't really see it get more ruby. You don't. You could see it on a colorimeter. If you had this strapped into a colorimeter, what you'd actually see is you have these. There's actually another color in there as well. Can't remember the actual color of it, but you see three peaks in the colorimeter. Looks like this, and that there is the yellow peak. Yeah, that's the yellow. And that's the Fe brackets H2O 5 brackets OH1, yeah, square brackets 2+. That's the yellow. This color down here is the ruby red, which we never really get to see. Yeah, that doesn't really there. But then there's also a third color there as well, because it's 3+, it can go again. But you don't need to worry about that one. That one's +1. There you go. They never ask about that one. They only ever look at this from a singular loss of H+, so you don't need to worry. But if you were then to put this and add acid, yeah, how would it shift? What would happen is the yellow peak would reduce and the ruby peak would increase. Yeah, that's what would happen. We'd probably still see it would probably turn more orange. Yeah, it'd be difficult to see the change. Okay, that brings us to the end of iron 3+. How amazing is iron 3? It's just yellow and brown all the way through. Love iron 3. That's why I can do iron 2 at the same time. So what does iron 2 do? Let's now look at iron 2. So Fe2+. Right. So once again, let's start off with iron 2 sulfate in this case. A white solid. Yeah, if it's anhydrous, it would be white. Yeah, difficult to get it, but it would be. Yeah, so iron 2 sulfate. Let's see if I can Google that. Ooh, curious. Anhydrous. Anhydrous. Iron 2 sulfate. Iron 2. I don't think it's going to like that. Should be spelled with an F as well. Oh, images. Anhydrous iron 2 sulfate. Oh, look at that. Almost. Ooh, ammonium. No, that's definitely not right. Anhydrous. It's so close to being white. So close. So close. Oh, hello. Almost white. Almost. Look, and they've sealed it in a tube, and it's still, you can see it's still oxidizing. It's crazy. Yeah. Okay, anyway. So, look at that. There's the anhydrous version of iron 3 sulfate, which is white, but it's because there's no water. You can see it going yellow, though. It's picking up water from the atmosphere. By the way, that property is called, it's a lovely word. It's one of my favorite words in chemistry. It's called deliquescent. Really lovely, long lost, forgotten word. The ability to absorb water from the atmosphere. So we've got a white. Always nice to add on our little white color. I quite like that. I was doing it like that. Yeah, there's the white anhydrous. Right, we're going to add it to water. Boom, I like it. Guys, you can see where this is going. So we've got H2O. We've got OH minus a little. We then have OH minus excess. Notice I've switched from sodium hydroxide to OH minus. It's the same process, but, I'm just trying to emphasize this, guys, that You know, they're going to ask you for things like reagents, ammonia excess. And when you say sodium hydroxide, then in the equation, of course, we're going to be looking at it from an OH minus perspective. So, okay, right, guys, off you go. So the first thing is I'm going to form the Hexa Aqua ion. We know this. Tick it if you got it right. And the color is green. A beautiful green color, pale green. Pale green. It's actually paler than that. It really is. It's nice to me to be able to give you like real colors. I'll show you. I'll send you the YouTube videos, guys, of the YouTube videos of these. Yeah, pale green solution. Right now, what's going to happen is we add OH minus a little, and it's going to its role. It's nice to mention, link all these things in. The role of OH minus here. Yeah, you guys can fill in that blank. Yeah, and the number of them. We remember that we're going to need 2 in this case, because the 2 plus requires 2 OH minuses. So we're going to form FeH2O4 brackets OH2. Cancels out the charge. We now have no charge, so it becomes a solid, and we form a snot green solid. Not particularly nice. Yeah. This is a lovely reaction because the pale green of the solution, you can actually dilute this to the point where you can't even see it. And then you can add sodium hydroxide and boom, this really dark green precipitate appears. And it just shows you that, you know, you could be drinking iron too and not even realize it was there. Now, at that point, it goes green and stays green. But now, we now add excess and things change. Yeah, we form the same thing. Whoops. We form the same thing. It doesn't redissolve. It doesn't redissolve because it's not acidic enough. But then the iron tree breaks that rule. Yet we form the same snot green precipitate. However, we are now in alkali conditions. Alkali conditions, because it's in excess. Yeah, alkali conditions. So what that means is it's now going to favor oxidation from the air. Favor oxidation. It's going to favor oxidation. And I'm going to end up with Fe brackets H2O3 close brackets OH3, and it's still neutral. This is important. It's going to become the precipitate we saw in the iron 3 one. It becomes that the Fe has gone from Fe2 plus to Fe3 plus and forms a brown precipitate. I wish we were in class just doing all of these practicals. It makes me so sad. I miss it. Cool, so that's gone through an oxidation process. And by the way, it happens at the surface. So if you have this in a test tube, what happens is you've got your pale green solution at the beginning. So your pale green solution at the beginning. You add your sodium hydroxide a little. You add your OH minus little. Yeah, and you form this snot green precipitate. Yeah. And by the way, they often refer to it as a gelatinous precipitate, PPT, a green gelatinous precipitate. And then what will happen is, if you just leave that, now if you do excess, nothing changes, it's still the same, but then what will start to happen is it will oxidize at the surface. So what you'll see is this, it'll start to turn, all the snot green precipitate will start to turn brown at the top. This is because the air is getting in and oxidizing it. Okay, next. Little's always the same, always nice. Always nice to have repetition in chemistry. Always nice. So with the little, it's roll. I wonder if no one's put the roll on there yet. Oh, come on, Sadoki. Come on. No charge, solid. Yeah. Its role, by the way, is a base. That's why the two littles are the same. Yeah, the role is the same. The little is acting as a base. And the ammonia, we know, can act as a ligand. It can act as a Lewis base. Yeah, where it donates a pair of electrons to form a coordinate bond. But in the little cases, it's acting as the same role. So we form the same snot green precipitate. And then on excess, it does identical as well. It does the same thing. It doesn't go through any ligand substitution. Very odd, none whatsoever. you form the same thing. And once again, it goes through the same oxidation process. No charge, solid, not green precipitate, but because we have now entered alkali conditions, because OH is in excess, it will oxidize to give me the same thing. Solid at the surface. The final one is iron 2 plus, unlike iron 3 plus, forms the carbonate. All 2 plus transition metals simply form their carbonate. And that one is a green solid. It's slightly paler. The iron 2 carbonate is slightly paler. They don't care. You just call it green. And that brings us to the end of iron 2, amazingly. There's no oddities either. You don't learn any of the... There are others that you can do with iron. There are others, like there are some beautiful iron complexes you can form. Ferrocyanate, that's always a great one. Or the hexacyano iron 3 complexes, blood red, I believe. Just gonna Google that one because I love some of those ones, and it's so rare. They never mention them, but it's nice to do so. So this is the hexacyano iron 3. They've called it ferrate. Images. Yeah, look at that, blood red. Isn't that beautiful? Yeah, it was one of the only methods of being able to get red back in the old days. If you didn't take the red color out of plants, if you wanted to make it synthetically and out of transition metals, it was one of the rare ones where you could make it, but it was immensely toxic, hugely toxic, scary toxic. So they didn't like to use it in anything, but it is a beautiful blood red. I've made that in class quite a few times with students. It's just such a beautiful color. I wonder if I can find a solution of it. Picture, yeah, no point. But yeah, there are others, but that's all you're expected to know from an iron 2 and iron 3 perspective. And we can tick off our learning objectives. So colors of iron 2 and 3, build the equations. We ought to do some, and then iron 2 oxidation we've definitely covered. So we can build some equations. What I'd like you now to do, guys, is I'm gonna pick several of these just randomly. I'm gonna pick the hard ones, the ones that I know everyone struggles with. So do that equation. And I'm going to pick the really hard ones. Oh God, and pick that one. Those two are the hardest equations you'll ever have to build in transition metal chemistry. What I'd like you to do is pause the video, please, and have a go at them. This is not an easy exercise, but very, very, very worthwhile doing. So pause the video and have a go. So we've got iron 3 plus with the carbonate ion. Okay, so question 1. So we're doing the iron Hexa Aqua 3 plus the carbonate ion 3 plus the carbonate ion. Now, the only benefit of these equations is the numbers are all pretty nice in terms of remembering them. Whenever I have the 3 pluses, I just remember there are 3 in the middle. All the 3 of them are balanced with a 3. There are just 3s everywhere in these equations. Yeah, so first thing I'm going to get is I'm going to get CO2 and water. And remember, I put the small people in the middle. Yeah, and I'm going to put 3s in front of all of them because I just remember the iron 3, the 3 pluses of anybody has 3 people in the middle and they've all been balanced with a 3. Right now, I remember that the 3 pluses are way too acidic. So that they're going to shred the carbonate ion. They're not going to form the carbonate itself. They're going to form the precipitate of the triaqua trihydroxy complex. So it gives me this. And so I'm going to see the observation. Of course, I've started off with a yellow solution, yellow sol, and I'm ending with a brown precipitate, brown PPT. I always forget, you've got to be careful about this one. By the way, state symbols included, there's not a solid there. So we've gone from a yellow solution, and we've formed a horrible brown precipitate, but we also need to balance for it, a 2 in here and a 2 in there as well, and now it all adds up. And as like you can see, I'm not so much building it. I'm building parts of it, but I also I've also put things into memory. These three are put into memory because it means it becomes so much more accessible in a reasonable amount of time. Because if you don't know this and you try and actually balance it and build it properly, then you just end up spending ages doing it, and there's a high likelihood of you getting it wrong. So it's worthwhile accounting that to memory. The next equation that I picked. So just give me, on the chat, please, give me a thumbs up if you got the equation correct. I know it was hard. Next one, the oxidation of iron 2+ precipitate to the iron 3+ precipitate using oxygen. Now that's tricky. So question number 2, we're going from iron 2+ precipitate, solid, and that's green. Not green precipitate. It is in contact with air in alkali conditions. Alkali cons. And what I'm forming is Fe H2O3 OH3 solid. And of course, this is the kicker. The oxygen always becomes water. That's the key thing. That's actually a really important fact in most transition metal chemistry. Redox catalysts, it always becomes water. Now we need to balance for it, and I never like balancing for these. So the nice thing is there's no electrons or charge anywhere, so I don't have to worry about that because it was a precipitate to a precipitate. So all I need to do is just count up my hydrogens. So over here, this here has lost 1 electron. Sorry, it's lost 1 H+. Now, when it lost the H+, it's lost a positive, but it's also then on the flip side, it's also lost a negative as well, hence the oxidation process. Yeah, because we know that this here is iron 2+, yeah, and this here is iron 3+, yeah. So it's lost a H+ and an electron to the water, to the oxygen. So what we now need to do is we need to say, well, hang on, if it's lost 1, and that's the key thing there, 1, just 1 hydrogen. Well, water requires 2. So what I'm going to need to do is I'm going to need to, I'm going to add on my color to the precipitate, by the way. Just suddenly realized I haven't added it. There you go. The horrible brown precipitate. So I need 2 hydrogens for the water. So I'm going to need to add a 2. I'm going to add these in bigger letters. I need 2 of them. So that's going to provide me now with 2 hydrogens for water. And then all I need to do is put a half in front of the oxygen, and I'm done. So the equations are challenging. They are difficult, and you've got to practice them. You have no choice. Practicing them is what makes it. But as I said, it's not just practicing them. It's understanding them. It's looking for that repetitive pattern, being able to apply that pattern. You still have to learn facts. I mean, it's A2 chemistry. It's the hardest chemistry you'll ever sit. But there are positives to take out of iron for sure. Build reaction equations. I'm going to leave the lesson there today, guys. Oh, my screen's flickering off and on. Why does the alkali condition cause it to react with the O2 instead of OH-? That's a really good question. Okay, well, hang on a sec. Hang on. So, okay, the answer is it's reacting with both, Julian. It's actually reacting with both. It's doing it simultaneously. So what's happening is okay, you don't need all this, but it's a great question. Here's what's actually happening. The iron, let's try and think about this in terms of why does the alkali condition favor it? If you're looking at this from an iron 2+ perspective, and we have 1, 2, 3, 4, 5, 6, and I go water, yeah, water, and then water, but then OH minus, and another water. So there's iron 2+. Yeah. So what we realize is happening is that in excess alkali, yeah, if you add all that together, because that's a minus and that's a minus, the overall charge on this complex is neutral. And that's now our green precipitate. Yeah, excuse me for not adding all my stupid hydrogens and making it 3D. There's our snot brown precipitate. Right, so if you have it in excess conditions, what will happen is that the OH minus that's in excess will actually still act as a base, and it'll take another one. Yeah, but when that happens, those electrons there rolling back, yeah, so we're going to form water. There's the water in the equation. Yeah, there's the water. But what then happens is that when that then breaks off, the electrons can actually drop all the way down to the Fe2 plus. No, hang on a second. No, it's the exact opposite, isn't it? At that point, the oxygen is able to react with the, I see what you're saying. Why doesn't it? The answer is it is doing. Oh, that's a good question. The answer is it does. But then the oxygen reacts with the OH minus. If oxygen reacts, if it reacts with water, what do you get if you half? It's not going to, is it? No, it's not. I can't really give you a solid explanation for that, Julian. Lol. Oxidation is favored in alkali conditions. It's acting as a catalyst, is what it's doing. Yeah, that is definitely overall what is happening. I wonder if I could find an answer to that online. I'm actually going to leave you to research that. Have a look into it. See if you can find a reasonable explanation for it, Julian. I'd really love to hear it. That's definitely your homework for today. Guys, I'm going to end my lesson there today. I love the fact that Julian's asked me a question which I'm struggling to answer. I haven't had that one. I muted it. There we go. Back to here. Right, guys, I'm going to leave you be now. Iron 2 and 3 is done. Not many to go now, guys. Nickel, aluminium, and that's kind of it. Guys, I hope you have a nice rest of your day, and I will see you soon. Bye now, guys.